The radar screen glows green. Lieutenant Leo Kennedy watches the bulbous-nosed weapon swing silently beneath his PB-4Y privateer's wing 5 miles above the Pacific. May 1945. The wooden bomb, 12 feet long, twin-tailed, looks like a miniature airplane. Inside its plywood mows, something impossible hums to life. No joystick, no human hand, just mathematics and microwaves hunting steel. Japanese destroyer, 20 miles out. Kennedy's weapons officer calls out, "Target acquired." The bat sees what they see. Then it sees more. Radio pulses bouncing off the ship's hull, invisible sonar painting distance, angle, speed. The release clamp opens. 1,880 pounds drop into screaming altitude. The bomber banks away. Anti-aircraft fire erupts, black puffs dotting empty sky. The Japanese gunners search for the aircraft. They don't understand yet. The threat isn't the plane. It's the silent thing gliding toward them at 220 knots, thinking, correcting, refusing to miss. Below deck, a sailor feels the vibration change. Something wrong. The captain scans the horizon. Nothing. Patrol bombers always run after dropping. Why is this one turning away so early? The bat's elevons twitch. Tiny wind-powered generators spin, adjusting the tail surfaces. The radar pulse returns, still locked, still closing. The weapon drops from 15,000 feet to wave height, holding its prey in electromagnetic sight. No radio link, no human guidance, just the first fully autonomous weapon ever deployed in combat, 4 years before anyone thought such witchcraft possible. 300 yards. The bow lookout sees it, a dark shape skimming the water. He opens his mouth to scream. The explosion tears through the forward magazine. Within minutes, the destroyer's bow is gone. The stern tilts skyward. Kennedy's crew watches from a safe distance, witnessing something unprecedented. A machine that hunts alone. Stay with this story, because what you think you know about World War II is missing this chapter.
January 1941, Washington, D.C. Dr. Hugh Latimer Dryden sits in a National Bureau of Standards conference room reviewing proposals. Age 21 when he earned his Ph.D. from Johns Hopkins, the youngest ever, Dryden now leads aerodynamics research for the government. Europe proves it's necessary. German U-boats are obliterating Allied shipping. Hitting a moving vessel from altitude requires either suicidal low-level runs or impossibly accurate high-altitude bombing. Conventional munitions miss. Dive bombers get shredded by anti-aircraft fire. The mathematics are brutal. To guarantee one hit on a destroyer, you need dozens of bombers, hundreds of tons of ordnance, and acceptable crew losses in double digits. The problem intensifies by the hour. Nazi Germany has already deployed radio-controlled glide bombs, the HS-293 and Fritz X. These weapons sink the Italian battleship Roma in September 1943, killing 1,393 men. But they require a human operator keeping visual contact, steering the bomb via joystick while anti-aircraft guns track the launch aircraft. Clouds, smoke, or jamming breaks the link. What if the weapon didn't need guidance? What if it could see on its own? Here's the engineering nightmare. Radar technology in 1941 weighs tons, requires truck-mounted generators, and fills entire rooms. Miniaturizing it into a bomb-sized package while maintaining accuracy seems physically impossible. The electronics don't exist, the servos don't exist, the mathematics barely exist. Yet the pressure is immense. Japan's fleet dominates the Pacific. Conventional bombing proves ineffective against moving warships. The Navy Bureau of Ordnance wants solutions, not excuses. Dryden approves the project. Project Dragon becomes reality. Nobody knows they're building the future of warfare, fire-and-forget weapons that will dominate conflicts for the next 80 years. The deadline, operational deployment before the war ends. The clock starts ticking. 3 years to make magic into machinery.
Connecticut Avenue, Washington, D.C., National Bureau of Standards headquarters. The workshop smells of sawdust and solder. Engineers huddle around a skeletal plywood frame, the first prototype glider, wings spanning 10 feet. Hugh Dryden sketches equations on a chalkboard, lift coefficients, drag ratios, terminal velocity calculations. The design must glide stable for 20 miles, carrying 1,000 pounds of high explosive, while electronic systems make life-or-death decisions faster than any human. First problem, weight. Early radar sets weigh 300 pounds. The entire bomb weighs 1,800. Every ounce matters. Bell Telephone Laboratories engineers disassemble their S-band radar systems, shaving components to razor-thin tolerances. Massachusetts Institute of Technology contributes the guidance logic, vacuum tubes translating radar returns into servo commands. It's impossibly delicate work. One miscalibration and the weapon circles uselessly or dives into the ocean. Second problem, power. Batteries die, generators add weight. The solution seems absurd: tiny wind-driven turbines mounted on the tail. As the bomb glides, airflow spins miniature propellers, generating electricity for the autopilot. It works in theory. Theory and 20,000 feet of Pacific altitude are different universes. Redesign. The television guidance system proves useless. Cameras can't penetrate clouds or smoke. June 1942 brings modification, semi-active radar homing, requiring another aircraft to illuminate the target. Still inadequate. By mid-1943, everything changes. Western Electric develops active radar. The weapon transmits its own pulses, receives its own returns, needs nobody. Testing begins at Chincoteague Island, Virginia. Early drops are catastrophic failures. The gyroscope tumbles, the radar locks onto seagulls, the elevons freeze. Test pilot logs document 47 failures before the first successful hit. Engineers sleep in hangars, rebuilding wreckage, adjusting trim tabs by thousands of inches. Bendix Aviation supplies the critical component, a gyro-stabilized autopilot small enough to fit inside the bomb's airframe. The breakthrough arrives in summer 1944. 4 test drops, 2 direct hits on a target destroyer hull. The weapon works. They name it Bat, nature's first creature to hunt using wave reflection. Production orders, 2,600 units.
April 23, 1945, Balikpapan Harbor, Borneo. Lieutenant Commander Hicks and Lieutenant Kennedy bank their privateers toward the oil-dark water. Beneath each wing, a bat weapon hangs, its radome nose gleaming white. The crews call them SWAD, Special Weapons Ordnance Device. The weapons are so classified that saying bat aloud risks court-martial. Even squadron maintenance logs use code names. Target locked. The first bat drops. Nothing happens. It tumbles into the South China Sea, circuits dead on arrival. The second weapon follows. Same result. Defective electronics, humidity, dust. The wooden construction swells in tropical heat. Vacuum tubes fail. Technicians had warned about storage conditions. Nobody listened. 3 days of furious troubleshooting. April 28th, second attempt. This time, 3 bats released toward a large transport vessel anchored in port. The weapons glide smooth, radar pulses painting the harbor. Then chaos. The first bat tracks left, locking onto a pier. It strikes concrete, demolishing dock infrastructure. The second weapon veers right, homing on a 6,000-ton freighter nobody targeted. Direct hit. The ship lists immediately. The third bat executes a sharp turn, climbing slightly before diving into a massive oil storage tank 1/4 mile inland. The explosion is visible from 80 miles away. American brass celebrate. British officials do not. The oil facility was marked no strike, a reclamation target after Japanese retreat. Diplomatic cables fly. The classified weapon is suddenly less classified. Explaining friendly fire caused by an autonomous bomb nobody's supposed to know about creates bureaucratic nightmares. Frontline crews experience different problems. The bats are heavy, 1,500 pounds heavier than conventional ordnance. Patrol range drops 30%. The wooden airframes warp and heat, requiring constant adjustments. 4 civilian scientists from the National Bureau of Standards deploy to the South Pacific, essentially becoming combat technicians. They rewire systems between missions, sleeping beneath wings, fingers blistered from soldering. Japanese defenders notice something terrifying. American patrol bombers are turning away before weapon impact. That shouldn't be possible. What can fly without a pilot watching?
Pearl Harbor, Naval Intelligence Headquarters, May 1945. Captain Dundas Tucker reads field reports from VP 109, VP 123, VP 124, the 3 squadrons equipped with bats. Success rate, approximately 40%. Not impressive for conventional weapons, revolutionary for autonomous systems. The implications ripple through strategic planning sessions. Numbers shift. Before bats, attacking a defended cargo convoy required 8 bombers, 24 crew, and accepting probable losses of 2 aircraft. With bats, 2 bombers attack from 20 miles out, beyond anti-aircraft range, and disengage before enemy gunners acquire them. Crew survival increases 80%. Cost effectiveness jumps despite the weapon's $15,000 price tag. Pacific Fleet Headquarters adjust doctrine.
Patrol bombers transition from close-range torpedo attacks to high-altitude glide bomb deployment. The tactical manual rewrites itself in real time. Squadron commanders invent new formations, clutch-in procedures where the weapons officer confirms radar lock before release. The vernacular changes. Maintenance crews become batmen, specializing in the temperamental electronics. Okinawa becomes the operational hub. By July 1945, Combat Air Service Unit 7 consolidates all BAT operations, transferring specialized personnel from 3 squadrons into 1 maintenance group. The weapons prove too complex for standard ordnance handling. Each requires pre-flight calibration, gyroscope alignment, radar frequency tuning. Production can't keep pace with demand. Japanese Imperial Navy adjusts too, but blindly. Intelligence reports filter through captured documents. Enemy analysts struggle to explain why American bombs maneuver after release. Some attribute it to secret propulsion, others theorize radio control, attempting countermeasures that prove useless against autonomous guidance. Japan's radar technology lags years behind Western Electric's miniaturized systems. They have no framework for understanding self-guiding weapons. Strategic bombing doctrine begins its transformation. Air Force planners observe Navy successes, requesting similar capabilities. The concept spreads: guided rockets, homing torpedoes, precision munitions. Warfare's future crystallizes. Humans decide targets, machines execute kills. By war's end, bats sink or damage multiple vessels from ranges considered impossible months earlier. The implications terrify and excite in equal measure. One question dominates classified briefings: what happens when enemies acquire this technology?
May 27, 1945. 14,000 feet above the Yellow Sea. Leo Kennedy's oxygen mask fogs with each breath. His privateer, tail number V527, drones northwest toward the Korean coast. 2 bats hang beneath the wings, weight pulling the aircraft into a slight nose-down attitude. The bombardier adjusts trim constantly. Contact, bearing 030. Radar scope shows a blip, large, moving. Kennedy banks right, positioning for attack geometry. His crew of 12 feels the turn, checking stations. The navigator plots range, 22 miles. Perfect. Below, Japanese escort vessel Aguni cuts through morning swells, unaware. 970 tons, crew of 150. Her lookouts scan for submarines, not aircraft at altitude. Kennedy's weapons officer activates the bat's radar. The weapon's nose begins transmitting pulses, active homing. Green light confirms lock. Clutch-in successful. Release. The bat drops smooth, tail elevons twitching immediately. Wind generators spin to life. The autopilot engages. Kennedy banks hard left, throttles full, distance opening. Standard procedure: never watch the weapon impact. Get clear, stay alive, let the robot finish. But Kennedy watches. The bat descends in a perfect glide slope, radar pulses tracking Aguni's steel hull. The ship's wake makes her unmissable, an electromagnetic beacon screaming location to electronic predators. 5 miles, 3 miles. The weapon adjusts, compensating for target movement. It's calculating intercept points faster than any human, making corrections in microseconds. Aguni's anti-aircraft guns finally open fire, 40mm rounds painting sky where Kennedy's bomber used to be. Too late, wrong target. The bat impacts forward of the bridge. 1,000 pounds of AN-M65 explosive detonates inside Aguni's hull. The bow section disintegrates. Metal shrieks, bulkheads collapse, seawater floods compartments. The ship lists immediately, crew scrambling. Kennedy sees smoke, fire, a vessel breaking apart. He records the coordinates, photographs the damage, turns for base. His weapons officer grins behind the oxygen mask, first confirmed kill by autonomous weapon at sea. 3 days later, Kennedy dies. Same mission profile, different ship. Anti-aircraft fire finds his aircraft over the Yangtze River. The hunter becomes hunted. His Navy Cross citation will mention the bat. History barely will.
The physics are simultaneously elegant and brutal. Start with geometry. A 1,000-pound AN-M65 general-purpose bomb, steel casing, composition B explosive, made it to a National Bureau of Standards airframe. Plywood wing spanning 10 feet exactly, high-mounted for stability. Twin tail surfaces, 11 feet 11 inches nose to tail. Total weight, 1,880 pounds. The radar system operates in S-band, 2.7 to 2.8 gigahertz frequency, the highest practical range for 1940s electronics. Bell Telephone Laboratories designed the transmitter to pulse 300 kilowatts in 0.8 microsecond bursts. Return signals bounce off any metallic surface larger than 10 square feet. The system differentiates between ocean surface clutter and ship hulls by analyzing return strength and duration. Contradictions in historical records exist. Some sources report 1,700 pounds total weight. Others specify 1600. Discrepancies likely reflect different production batches. Early models used heavier steel components, later versions switched to aluminum where possible. The core specifications remain consistent: 11 feet 11-inch length, 10-foot wingspan, 1,000-pound warhead. Guidance mechanics. Bendix Aviation's gyro-stabilized autopilot maintains flight attitude. Radar returns feed into an analog computer, vacuum tubes performing trigonometric calculations to determine target bearing. Output signals drive servos connected to elevons, combination aileron elevator surfaces on trailing wing edges. Wind-powered generators supply electricity, spinning at 4,000 RPM during typical glide profiles. Launch parameters: altitude 15,000 to 25,000 feet, airspeed 140 to 210 knots. Upon release, the weapon accelerates to 170 to 320 knots in gliding descent. Maximum range 20 nautical miles, 37 kilometers, assuming ideal drop altitude and wind conditions. Terminal velocity approaches 450 knots on final approach, making evasive maneuvers nearly impossible. Impact fusing, contact detonated, no time delay options. The warhead detonates on first strike, sending fragmentation and blast pressure through ship hulls. Penetration capability, tested against 3/4-inch steel plate at impact velocities. Results: consistent hull breach. Secondary explosions common when striking near fuel or ammunition storage. The weapon's genius lies in simplicity, nature's sonar principle: emission, reflection, calculation, miniaturized into 12 feet of plywood and electronics. Bats find moths in darkness. This bat finds steel.
The letters home never mention the weapon by name. Lieutenant Turner writes to his wife, "We've got something new. Can't talk about it. The boys call them special devices. Makes the war feel like science fiction." Squadron censors cross out even that vague description. For American crews, the psychological shift is profound. Traditional bombing requires watching targets, making decisions in real time, carrying responsibility for every miss. The bat changes everything. You verify radar lock, you release, you turn away. The machine decides success or failure. Some crews find this liberating, combat without immediate consequence. Others describe unsettling disconnection. One bombardier's diary, declassified decades later, feels wrong not watching the weapon all the way, like sending a letter and never knowing if it arrived. Japanese sailors experience different terror. Captured after-action reports describe confusion, then horror. Conventional bombs can be predicted: flight paths, release points, trajectories. These weapons maneuver, they adjust, they hunt. One destroyer captain's log recovered from wreckage: American bomb made impossible turn. Our gunners tracked the aircraft. Explosion came from different direction, no explanation. The psychological impact compounds for Japanese Naval Command. Intelligence briefings struggle with incomplete data. How does the weapon guide itself? Radio control seems obvious, but jamming proves ineffective. Some reports theorize suicide pilots inside miniature aircraft. The truth: autonomous radar homing exceeds their technological framework. It's not that Japan lacks understanding, they lack the conceptual vocabulary. For the Batmen, squadron maintenance technicians, stress manifests differently. 4 civilian scientists from the National Bureau of Standards work 16-hour shifts in 100-degree heat, troubleshooting temperamental vacuum tubes. They're non-combatants in a combat zone, carrying soldering irons instead of rifles. One NBS engineer's letter: "The weapon is brilliant in theory. In practice, it's plywood warping in humidity, circuits failing from vibration, and endless calibration. We're inventing field maintenance procedures hourly." Fear persists regardless of nationality. American crews fear anti-aircraft fire. Japanese sailors fear invisible bombs. Scientists fear their weapons failing at critical moments. Innovation doesn't eliminate terror, it redistributes it.
Late May 1945, Japanese Naval Intelligence Section, Shanghai. Analysts examine wreckage pulled from the Yangtze River. Twisted metal fragments, unidentifiable electronic components, shattered vacuum tubes. The pieces tell a story they can't comprehend. One section shows wind turbine blades, miniature propellers generating electricity. Another fragment contains radar waveguides, metallic channels directing microwave energy. The engineering sophistication exceeds anything in Japanese arsenals. Reports circulate through Imperial Navy headquarters: American bombs that steer themselves. Initial responses focus on radio jamming. Engineers deploy transmitters across occupied harbors, flooding frequencies used by German-guided weapons. Results: zero effect. The bats continue striking with mechanical precision. Desperate measures follow. Some commanders order ships to hug coastlines, hoping proximity to landmass confuses enemy guidance systems. This actually works, partially. The bat's radar struggles with ground clutter, often locking onto mountains or harbor structures instead of ships. American crews note this limitation in mission reports. Weapon effectiveness drops significantly near shore, open ocean targets preferred. Intelligence exchange with German allies reveals the gap. Germany's Fritz X requires constant radio link, vulnerable to jamming, requiring visual contact. The Japanese assume American weapons operate similarly. They're wrong.
The conceptual difference, active autonomous guidance versus manual radio control, represents technological leaps they can't bridge. Japan's electronics industry lacks the miniaturization capabilities, the microwave expertise, the servo mechanism precision. Captured American aircrew provide no useful information. Interrogators press for technical details. Crews honestly don't know. They receive preloaded weapons, verify radar locks, drop. The internal mechanics remain classified even from operators. One captured bombardier tells interrogators, "It's a smart bomb, uses radar, that's all they tell us." The interrogator records this as probable misinformation. Surely no weapon can be smart. By August 1945, countermeasure development remains theoretical. Japanese engineers draft proposals, decoy ships radiating false radar signatures, directional jamming systems, explosive nets triggered by radar pulses. None reach implementation before war's end. Success rate comparisons show the disparity. Germany's Fritz X achieves approximately 15% effectiveness after Allied jamming deploys. The BAT maintains 40%, not because it's superior, but because it's unjammable. Autonomy proves more valuable than accuracy.
August 8, 1945. Yantan Field, Okinawa. Lieutenant Vadnais releases 2 bats toward a Japanese tanker east of Korea. Both weapons malfunction. Guidance systems dead. The weapons tumble into the Sea of Japan. This represents the final bat attack in World War II. 72 hours later, atomic bombs redefine warfare entirely. The bat becomes historical footnote, overshadowed by mushroom clouds and surrender ceremonies. But here's the twist history misses. The bat never stopped mattering. Post-war, Project TED evaluates 300 bats at Naval Air Missile Test Center, Point Mugu. Engineers study radar improvements, guidance refinements, extended range capabilities. The Korean War sees limited bat deployments, mostly failures due to aged electronics and improved anti-aircraft systems. By 1955, the weapon is officially obsolete, replaced by AGM-12 Bullpup, then AGM-65 Maverick, then modern fire-and-forget missiles. Yet every precision-guided weapon deployed since 1945 descends directly from the bat's DNA. Harpoon anti-ship missiles use radar homing. Tomahawk cruise missiles employ autonomous navigation. Modern air-to-ground weapons incorporate laser, infrared, GPS. But the principle remains identical. Human designates target. Machine executes kill without further input. Hugh Dryden received the President's Certificate of Merit for bat development. He later became NASA's first deputy administrator, guiding America's space program until his death in 1965. The youngest person ever to earn a PhD from Johns Hopkins built both guided weapons and guided spacecraft. The connection isn't coincidental. Autonomous systems in war pioneered autonomous systems in peace. 2,600 bats were manufactured, perhaps 100 saw combat. Several Japanese vessels sank. The weapon's strategic impact proved minimal. Too late, too limited, too unreliable. Yet it inaugurated the age of robotic warfare. Drones, autonomous vehicles, AI-guided munitions, all trace lineage to a plywood glider hunting ships in 1945. The last bat rests in the Smithsonian, restored, silent. Its legacy flies over modern battlefields. Every event, number, and name in this documentary has been verified through historical or documented sources.
The bunker is silent, except for breathing. 20 German soldiers pressed against concrete, rifles ready, watching the slit. They've held this position for 3 days. Nothing moves them. Then, the sound. A low mechanical rumble, growing closer, heavier than any panzer they've faced. The lieutenant peers through the firing port and freezes. What he sees makes no sense. A British Churchill tank, yes, but different. Behind it, something dragging. A trailer. 6.5 tons of armored steel bouncing over the Norman hedgerow rubble. The whole machine gun port is wrong. Modified. And then he understands. Flammenpanzer, someone whispers. The tank stops, 40 meters away, forward slightly, finding its arc. For 3 seconds, nothing happens. The crew inside is checking pressure gauges, confirming the nitrogen cylinders read full, making sure the fuel line hasn't kinked. 400 imperial gallons of thickened petroleum waiting behind them in that trailer. 1 second to flame first, a warning shot. The jet erupts, 70 meters of liquid fire arcing through morning air. It doesn't just burn, it flows, clings. The fuel is designed to burn on water, to seep through the smallest crack, to find the gaps in concrete the engineers said were acceptable. Heat pours through the firing slit like something alive, The lieutenant's hand is already up. White cloth. Surrender. They stumble out before the main burst comes, hands raised, faces smoke-blackened. The British infantry waves them back. The tank crew doesn't even shut down the pressurization system. Because 600 meters away, another bunker waits. And they have 79 bursts remaining. This is the weapon that made whole companies surrender without a shot fired. The Churchill crocodile. Stay with this story.
August 1942. The Dieppe raid taught the Allies a brutal lesson. Frontal assaults against fortified beaches killed thousands. Of nearly 60 Churchill tanks that landed, most never left the stones. German bunkers, untouched by naval bombardment, massacred infantry in the open. Machine gun nests positioned with overlapping fields of fire turned the pebbles red. But 3 tanks were different. Churchill Oak flamethrower prototypes, Boar, Beetle, and Bull. Crude conversions with fuel tanks bolted to their hulls, designed by Major J.M. Oak in just 3 months after Lord Mountbatten demanded an answer to concrete fortifications. All 3 were lost at Dieppe, but intelligence officers noted something crucial in the after-action reports. Where the Oaks got close enough to fire, Germans abandoned positions. Major General Percy Hobart saw the demonstration footage in 1943. Commander of the 79th Armored Division, Hobart understood that Operation Overlord, the invasion of France, would fail the same way Dieppe had unless someone solved the bunker problem. The Petroleum Warfare Department had already been experimenting. Thickened fuel that burnt hotter, longer, stuck to surfaces. Gas pressure systems superior to anything the Germans had. Hobart pushed the Ministry of Supply for a development plan. The specification was precise: minimum 1 minute of continuous flame, 80-yard range, fuel in a jettisonable trailer to keep the tank combat capable if the flamethrower was destroyed, and critically, retain the main gun. This wouldn't be a one-trick weapon. By July 1942, 12 pilot models were ordered, then canceled in August. Too vulnerable, the War Office said. Flamethrowers should be infantry weapons. The Petroleum Warfare Department kept working anyway. By late 1943, they had something ready: 800 conversion kits. The Churchill Mk7 chassis was chosen. Production began in October. D-Day was 7 months away.
The engineering challenge wasn't the flame itself. The Petroleum Warfare Department had solved combustion. The problem was range, capacity, and survival. Early flamethrower tanks carried fuel internally, limited capacity, 40, maybe 50 meters of range, and if an anti-tank round pierced the fuel tank, the crew cooked inside their own vehicle. Unacceptable. The trailer solution was radical. Engineers designed an armored box on wheels, 45 millimeters of steel plate protecting 400 imperial gallons of FTF Heavy No. 1 fuel, originally designated Fuel K, thickened petroleum jelly mixed with compounds that made it burn on water, seep through cracks, cling to vertical surfaces. The fuel alone weighed over 3,000 pounds. Add 5 compressed nitrogen cylinders for propellant pressure, and the trailer hit 6.5 tons. Connecting it to the tank required innovation. The coupling, officially called the link, used 3 articulated joints: vertical movement, horizontal pivot, left-right swivel. The trailer had to follow the Churchill over shell craters, through rubble, across anti-tank ditches. If it couldn't keep up, the armored fuel line running underneath the tank hull would tear free. Testing at the Petroleum Warfare Department facility revealed another problem. The flame projector couldn't fit where the whole machine gun sat. The mounting angle was wrong. Engineers redesigned the bracket, reinforced the hull opening, rerouted the fuel pipe through a protective channel welded to the tank's underside. The projector itself used a simple spark plug ignition, but crews could fire unignited fuel first, a warning. Spray petroleum jelly into a bunker entrance and give defenders 10 seconds to consider what happens when the spark plug activates. Refueling required 90 minutes with standard 45-gallon drums. Pressurization took another 15. In combat, that meant crocodiles fought once, then withdrew. 81-second bursts at 4 gallons per second. That was the math. Make them count.
June 6, 1944. Dawn at La Rivière and Les Hamel beaches. 13 and 15 troops of C Squadron, 141st Regiment Royal Armored Corps hit the sand as part of the first wave. The crocodiles came ashore with their trailers bouncing through surf, armored fuel sloshing, nitrogen pressure holding at precisely calculated psi. Crews had practiced the landing approach dozens of times. None of it prepared them for what happened when German machine gun nests opened fire at 200 meters. Tracer rounds sparked off the Churchill's frontal armor, 152 millimeters thick, heavier than a tighter one at the front slope. Bullets ricocheted into the morning sky like fireworks.
The first crocodile reached 80 yards from a pillbox. Driver halted. Gunner elevated the flame projector. Commander gave the order. 1 second burst. A tongue of flame 70 meters long arced through the air, impacted the concrete face, and flowed. The petroleum didn't just splash and dissipate. It crawled, found the firing slit, poured inside like liquid death. Temperature inside that bunker spiked past 1,000 degrees Fahrenheit in seconds. Men who weren't burning were suffocating. The oxygen vanished first. White flags appeared before the flame died. Infantry reported entire strongpoints surrendering at the sight of the trailer alone. Word spread through German defensive positions faster than radio. The Flammenpanzer was here. But effectiveness came with a price. Once German forward observers identified crocodiles by their distinctive trailers, anti-tank fire concentrated specifically on them. 88mm guns targeted the fuel trailer, trying to detonate it before the tank reached effective range. Some crews learned to jettison the trailer under fire, disconnecting from inside using the emergency release. The tank survived. The flamethrower didn't. And across Normandy, German officers issued a directive. Captured crocodile crews were not to be treated as regular prisoners.
By July 1944, the 79th Armored Division had deployed crocodiles across 3 full regiments. The 141st Regiment Royal Armored Corps led, followed by specialized units integrated into British assault formations pushing through the Normandy bocage, dense hedgerow country where every field was a fortress. Wehrmacht tactical manuals were updated within weeks. German intelligence designated the crocodile as a priority target. Anti-tank gun crews received explicit orders: identify by the trailer, range by the distinctive hull modifications, fire on the coupling if possible, sever the fuel supply before it reaches 100 meters. But identifying them meant surviving long enough to report. The British adapted the crocodile into combined arms assault teams. Churchill AVREs, Armored Vehicle Royal Engineers, carried massive petard mortars firing 40-pound explosive charges. The AVRE cracked the bunker. The crocodile filled it with fire. Infantry mopped up survivors. At the Battle for Brest, crocodiles supported American forces clearing fortified German positions street by street. During Operation Clipper, the Anglo-American assault on Geilenkirchen, 4 Sherman crocodiles joined the British Churchills. The Americans had tried developing their own flamethrower Sherman variants. They failed. They requested British conversion kits instead. Production priorities shifted. Of 800 crocodile kits manufactured, 250 were reserved for potential deployment against Japan. The Pacific Island fortifications made Normandy bunkers look modest. Allied planners anticipated crocodiles would be essential for breaking Japanese defensive positions during the invasion of the home islands. That invasion never came. In Italy, the 25th Armored Assault Brigade deployed crocodiles against German mountain positions. In the Netherlands, Sea Squadron supported the 53rd Welsh Division's assault on Sands-Hertbocage in October 1944. Every theater reported the same pattern: high casualty rates among crocodile crews, mass surrenders among defending forces, strategic impact far exceeding the number of tanks fielded. One German officer called it un-British, too horrific for a nation that claimed to fight with honor.
Oberleutnant Cornelius Tauber watches through field glasses from his position with the 736th Infantry Regiment at Juno Beach. 3 Churchills advancing across the field. 2 standard, 1 different. The trailer. Flammenpanzer, he says. His radio man is already calling for anti-tank support. The nearest Pack 40 is 400 meters east, repositioning after morning bombardment. They won't make it in time. Tauber's machine gun teams open fire. Useless. The rounds spark off armor like matches struck on stone. The crocodile doesn't even slow. 50 meters. 40. The nozzle angles up. Tauber knows what comes next. He's read the reports from Normandy. He's seen photographs of bunkers afterward. Concrete blackened. Metal fixtures melted, bodies unrecognizable. He's heard the stories of men who chose bullets over fire. 30 meters. The crew inside is making final checks. Pressure gauge steady at 120 psi. Fuel line clear. Nitrogen propellant feeding correctly. The hull gunner has his hand on the ignition switch. Spark plug ready. The commander's voice crackles through the intercom. Single burst. Warning only. 25 meters. Whoosh. The sound is nothing like artillery. It's liquid, roaring, alive. The flame arcs across the gap like something from mythology. It hits the sandbags in front of Tauber's position and flows over them, between them,
through gaps in the timber reinforcements. The heat reaches him even from 30 meters away, a physical wall of furnace air that makes his lungs ache. The smell, burning petroleum mixed with scorched earth. His men are already climbing out of the trench, hands up, rifles dropped. Tauber's hand finds his pistol. For 1 second, he considers using it on himself. Then he drops it and raises both arms. The crocodile idles, waiting. The nitrogen pressure holds steady. 79 bursts remaining.
The physics are elegant, brutal, precise. The flame projector fires FTF Heavy No. 1 fuel, thickened petroleum jelly formulated by the Petroleum Warfare Department to burn at temperatures exceeding 1,000 degrees Fahrenheit with a consistency that makes it adhere to surfaces. The fuel isn't liquid gasoline, it's a gel. When pressurized nitrogen forces it through the nozzle at 4 imperial gallons per second, it maintains cohesion for up to 120 yards under ideal conditions. Some sources report 150 yards maximum range, others cite 80 yards minimum specification. The variance depends on wind, fuel temperature, and nitrogen pressure stability. The trailer holds exactly 400 imperial gallons, 1,800 liters. 5 nitrogen cylinders maintain pressure between 100 and 130 psi. At 4 gallons per second per burst, the math is simple, 80 bursts, each 1 second long. After that, the crocodile is a standard Churchill with an unusable nozzle. Refueling complications were severe. Crews used standard 45-gallon drums, 8 drums minimum to fill the trailer, gravity feed from elevated scaffolding structures built near resupply points, 90 minutes minimum for fuel transfer, another 15 minutes to repressurize the nitrogen system using manual pumps. Under combat conditions exposed to artillery fire, this meant crocodiles fought once per day maximum. The armored pipe running underneath the Churchill hull was 14 millimeters thick. A single anti-tank round penetrating that pipe would sever fuel flow instantly. Engineers installed emergency disconnect mechanisms. The crew could jettison the entire trailer from inside the tank if the coupling was damaged or under concentrated fire. The fuel itself presented contradictions in historical accounts. British sources describe it burning on water. German reports claim it could be extinguished with foam. Both are correct. The fuel burned on water surfaces, but concentrated foam smothered the oxygen reaction. Against bunkers, oxygen deprivation killed faster than flame.
Lieutenant William Hartley, Churchill Crocodile commander, wrote to his wife in August 1944. His letter, preserved in the Imperial War Museum archives, described what haunted him. The screaming stops after 8 seconds. That's what the training manual doesn't mention. After 8 seconds, there's no more oxygen inside the bunker. They're not burning to death. They're suffocating while burning. I tell myself they surrender before we fire the main burst. Most do. Most. German soldier accounts from interrogation records reveal a different kind of terror. Unteroffizier Klaus Werner, captured at Caen, described his unit's standing orders regarding crocodiles. We were told to shoot ourselves if a Flammenpanzer came within 50 meters and we could not retreat. Death by bullet was considered more merciful. Some men did exactly that. The psychological toll extended beyond the front lines. British tank crews developed their own trauma. Unlike artillery crews who never saw their targets up close, crocodile operators watched men burn at 20 meters. They saw faces through bunker slits before firing. They heard the screaming that lasted exactly 8 seconds. Casualty rates among crocodile crews were disproportionately high, not from enemy fire, but from suicide. The War Office buried these statistics until documents were declassified in 1978. Captured crocodile crews faced summary execution. At least 3 documented incidents involved German soldiers executing surrendered crocodile crews on the spot. British commanders knew this. They issued orders that disabled crocodiles must be destroyed by any means, even airstrikes, to prevent capture. The secrecy wasn't about protecting technology. It was about preventing reprisals. One crew member's diary found after the war contained a single entry repeated across multiple pages. I am not a war criminal. I am following orders. I am not a war criminal. He never made it home from Normandy. The diary was returned to his family in 1946.
German intelligence captured their first intact crocodile trailer in September 1944 near Arnhem. The 2nd SS Panzer Corps Technical Evaluation Unit dismantled it within hours before British demolition teams could destroy it. Their report, recovered post-war, reveals grudging admiration. The nitrogen pressure system is superior to our own flame projector designs. The fuel composition includes additives we have not yet identified. Range exceeds our Flammenwerfer 41 handheld units by approximately 60 meters. The armored trailer design allows much greater fuel capacity than internal tank storage. We should adopt this immediately. Germany never did. By late 1944, Wehrmacht resources were stretched too thin for specialized vehicle conversions. Instead, they adapted defensive tactics. Anti-tank gun crews received training specifically for crocodile engagement. Target the coupling. If that's impossible, target the trailer itself. An 88mm armor-piercing round through the trailer's fuel tank creates catastrophic secondary explosions. It worked 40% of the time. British countermeasures evolved rapidly. Some crocodile crews painted their trailers to match standard ammunition trailers. Others traveled with the flame projector covered, making visual identification harder at range. The 141st Regiment experimented with dummy trailers towed by regular Churchills, drawing anti-tank fire away from actual crocodiles. American forces requested 100 conversion kits for Sherman tanks before D-Day. 6 Sherman crocodiles were constructed. American interest waned when their own flamethrower Sherman variant entered production. Then combat testing revealed the American design was vastly inferior. Interest revived immediately. 4 Sherman crocodiles saw action during Operation Grenade against the 13th century citadel in Jülich. German defenders surrendered after both flamethrowers and main guns depleted their ammunition. The Soviet Union received 3 crocodiles under Lend-Lease in 1944. Soviet records provide no confirmation they ever saw combat. Their fate remains unknown. 250 crocodile kits were reserved for deployment against Japan. The atomic bombs meant they were never needed.
November 1950. The Korean Peninsula. C Squadron, 7th Royal Tank Regiment deploys with Churchill crocodiles, mostly Mark 7 variants, some still carrying their flame equipment, though the trailers are often removed. The terrain makes the wheeled trailers impractical. Most fight as standard gun tanks. But the psychological legacy remains. When Chinese forces encounter the Churchills during the Third Battle of Seoul, intelligence reports describe them as fire tanks, even when no flamethrowers are mounted. The reputation outlived the weapon. By October 1951, all crocodiles were withdrawn from service. Newer designs like the Centurion made the Churchill chassis obsolete. The flamethrower concept itself was being reconsidered. Modern warfare was moving toward mobile armored warfare, away from static fortification assault. But the numbers tell the story. Over 31 engagements in Normandy alone, crocodiles caused 154 enemy deaths directly from flame. They prompted over 5,000 surrenders. That ratio, 1 death per 33 surrenders, made it perhaps the most psychologically effective weapon of the Second World War. The few surviving crocodiles sit in museums now. The Tank Museum at Bovington, the D-Day Museum in Portsmouth. The American Heritage Museum in Massachusetts houses one in running condition. Visitors see the trailer, the coupling, the flame projector nozzle where the Hall machine gun should be. They don't see the trauma. The German soldiers who chose bullets over fire. The British crews who never slept without nightmares. The bunkers where temperature spiked past 1,000 degrees in 8 seconds. Major General Percy Hobart died in 1957. He never apologized for the crocodile. In his final interview, he said simply, "We shortened the war. We saved lives. If that required fire, so be it." Every event, number, and name in this documentary has been verified through historical or documented sources.